In this video, we're going to discuss the multiplicities of roots. Now, there is a little bit of previous knowledge you're going to need for this. You need to understand the end behavior of polynomials. So just kind of think back to when we studied those. We saw that if a degree of a polynomial is even, the ends moved they move together either both up or both down, depending on if the leading coefficient, which we called the an, was positive or if it was negative. Now, if the degree is odd, we saw the ends moved away from each other. Is either increasing or decreasing. Again, depending on if the leading coefficient was positive or if it was negative. Now, what we said, though, is we don't know what happens in the middle. So we erased the middle bits and we put dotted lines in there to signify that something's going on there, but we don't really know what. And so that's what we're working to study today. We want to understand what's going on in the middle. And so to do that, we need to find the x-intercepts, the roots of a polynomial, along with the y-intercepts that help as well. So let's start with an example. Let's take f of x to be equal to x squared plus 3x plus 2. This polynomial is in general form. We can see that the degree, I'm going to call the degree n, the degree is 2, the leading coefficient is 1, importantly is positive, and because of that, I know that this thing opens up. I know this is quadratic, in fact, so we probably could graph it based on it being quadratic, but let's take this new approach to the degrees leading coefficients. So now we want to understand what's going on in this dotted area in the middle of this function. So we need to be able to find the x-intercepts. Let's do that next. X-intercepts, we're going to take a polynomial, we're going to set it equal to 0. Now keep in mind I'm saying x-intercepts, but it might be that we find we don't have x-intercepts. They might be imaginary numbers, meaning we have roots. So I'm factoring it. I realize the factors of 2 are 2 and 1. 2 and 1 gives me a 3x. So I factored it correctly into my x-intercepts negative 2, negative 1. And that fits because, in fact, what we're going to see is the number of roots should correspond to the degree of the polynomial. So we had a degree 2 polynomial, we see 1, 2 roots here. Now, I'm not saying anything about unique roots, different numbers, but the number of roots should always correspond to the degree of the polynomial. So now we actually know what this thing looks like. On the xy axes, we have x-intercept at negative 2 and at 1. It's going to pass through both of those. And there's my polynomial. Not still perfectly accurate because it really would have been a good idea to find the y-intercept as well. The y-intercept, that's very easy. Plug 0 in for all the x's, we get the y-intercept to be 2. Should not be symmetric about that point. Should be, try and draw that bottom a little bit better. And so right there, that would be 2. So we've gotten an approximation of what that center looks like. We knew from before the ends went up, and now we have our x-intercepts and our y-intercepts stuck in there. Let's take another example. Let's take g of x to be x squared plus 2x plus 1. I'm going to go ahead and factor this because I want to know the middle bit. So I'm going to have x plus 1, x plus 1. That's my function, and if we're trying to find the x-intercepts, I'm going to go ahead and set that equal to 0. So I get my x-intercepts to be negative 1, and it occurs twice. Let's go back and talk about the degree and leading coefficient for a minute. The degree was 2, the leading coefficient positive, tells me that it should be a parabola opening up. But if we have an x-intercept of negative 1, how is that going to work? If I want to cross through the x-axis, say we cross on the way down, well, I'm going to have another x-intercept, so that's not possibly going to work out. So maybe it's on the way back up. So if that negative 1 is what we pass through on the way back up, that's still not going to work because we have another x-intercept over here, and we didn't see that we had another one. We only had that one x-intercept. Moreover, this breaks the rule that I just told you that the number of x-intercepts, the number of roots, should correspond or should match the degree of the polynomial. In this case, we should have had 2. And that wasn't true. So what that tells us, and what we see here, is we actually had that negative 1 twice. It was a root. It's a root twice over, negative 1. And so what that tells us is our quadratic function is sitting on that x-intercept of negative 1. It touches that negative 1 and then turns back around. So we see two important concepts here. We see that roots, in this case an x-intercept, but roots in general, sometimes occur more than once. And this is where we get to that term, the multiplicity of a root. The multiplicity of a root is the number of times the root occurs. So in that previous example, that -1 had a multiplicity of 2. In the example previous to that, the one before that, we had 2 roots with multiplicities of 1. So if we take a couple polynomials in factored form, because it's easier to see the roots in factored form, let's take a polynomial x plus 1, x plus 3 times x minus 2. So x plus 1, x plus 3, x minus 2 all being multiplied. Very easy to see that our x-intercepts, our roots are -1, -3, and +2. Each of those is in a factor just once, so they all have a multiplicity of 1. Let's take another polynomial, g of x, and let's say this one has a factor of x plus 1 squared, x minus 2 to the third, x plus 1. So this time we have x-intercepts of -1/2, of +2, and of -1. Their multiplicities, the multiplicity of the -1/2 was 2 because 2x plus 1 had an exponent of 2 on it. That was a factor twice, so that gives us that root of -1/2 twice. The 2 has a multiplicity of 3 because x minus 2 was a factor 3 times over, so we'd have to set that equal to 0 3 times over and get it as a solution 3 times. The -1 has a multiplicity of 1 because it just occurred once, that factor just occurred once. So once we understand the multiplicities are very important. What we saw in that example, the x squared plus 2x plus 1, that -1 caused the function to look a little different. Let's just recall x squared plus 2x plus 1. We saw it as a polynomial, and we saw it was sitting on the -1. It touched and turned at that point -1. So what multiplicities tell us, no E in there. What the multiplicity tells us is if the multiplicity is even, the graph will touch and turn on the x-intercept. If the multiplicity is odd, the graph will pass right through. Okay, so let's take an example. F of x, I'm going to give this one factored form again. So we'll take x minus 1, x plus 2 squared, and x minus 3. So we have x-intercepts. Let me do it in a table form this time. So our x-intercept of 1, -2, and 3. Our multiplicities on those would be 1, 2, and 1, because we had x minus 1 as a factor once, x plus 2 as a factor twice, x minus 3 as a factor once. Now, notice something just to recall. I said the degree of the polynomial should match the number of x-intercepts, the number of roots. In this case, the degree, we had 1 factor here, 2 factors here, 1 factor here, so the degree of the polynomial would be 4. 4. And if we add those multiplicities, those add to the degree. So the sum of the multiplicities must add to the degree of the polynomial. So if we want to do the graph of this, the degree is 4, it's even, so we know it's going to open up or down. The leading coefficients, the coefficients on all the x's were positive, so that means our leading coefficient is going to have to be positive. So it's going to have the end behavior where it opens up. And now we can plot the x-intercepts, the 1, the -2, and the 3. The graph's going to approach that first x-intercept. It's going to hit it. Because the multiplicity was 1, it's going to cross at that 1. It's going to pass right through it. At some point, it's going to turn around. It's going to come back up to that. I plotted the wrong one there. Excuse me. So if we look at the first one, I have my list out of order. The -2. The -2 is first. That had a multiplicity of 2, so it should actually touch and turn, or bounce. So we're going to get to the -2, we're going to touch and turn off of that. some point our function is going to turn around. The next intercept we're approaching is the 1. That had the multiplicity of 1. That's going to cross at that point. It's going to go right through the 1. And then at some point it's going to turn around. And it's going to approach the 3. And when it approaches the 3, because that multiplicity is 1, it's going to pass right through. So notice our end behavior has worked out correctly. Both the lines are opening up. We had to know what it was going to approach from the left, but we can always check that right line by checking based on the multiplicities. Let's do one more. Let's take h of x to be the polynomial x minus 1 times x plus 3 to the 5th, and we'll do x plus 4. So if we set up our x-intercept table again, we're going to have x-intercepts of 1, -3, -4. So this time they're kind of completely backwards, completely out of order. Their multiplicities, to clean that 5 up, that was a 5 on the x plus 3. So our multiplicities on the 1 was a 1, -3 had a multiplicity of 5, and x plus 4 had a multiplicity of 1. So as far as what that tells us, they're all going to cross. All going to cross because all the multiplicities are even. Again, remember we're looking at the multiplicities, not the x-intercepts. It doesn't matter what the x-intercept number is. We want to know the multiplicity number. If it's odd, it crosses. If it's even, it bounces. The degree of the polynomial, just so we know our end behavior, the degree was 7. We can see it either by counting the factors. There's 7 factors, or we can count the multiplicities, 7. They should work out to be the same. Good way to double check ourselves. Leading coefficient, if we look at all the coefficients inside the factors, they're all positive, so our leading coefficient is going to be positive. So we know this thing is going to be increasing and the ends are going to go away from each other. So if we plot this polynomial, let's start by putting the x-intercepts on there. 1, -3, and -4. So we're going to start by approaching from the low left because that's what the end behavior tells us to do. When we get to that -4, we're going to pass right through it. Then we're going to at some point turn around. We're going to hit that -3. We're going to pass through that as well. And then we're going to pass through the 1. And so that's our function. Notice we can check the end behavior, and it is going up to the right at the end. So the last question is, if they all cross, why does it matter if the exponents are higher? Why does it matter if one's a little bit lower or higher than another? So I did a little bit of a disservice. I kind of skimmed over it because I wanted to make sure we understood when things crossed and turned first. But actually, these tell us a little bit more beyond just crossing and bouncing. The higher the degree, or the higher the multiplicity, the higher the multiplicity, the more the graph will flatten out. So at -3 here, what we're going to see is, if we're to really zoom in on our graph, we notice it flattens out a little bit at that point. And that makes sense just based on what we know about x and x cubed. We said both of these are odd degree polynomials, means they both are going to go from low left up right if we view the positive cases. The only difference in them is their degree, or in this case, because they're just simple single term polynomials, then we're looking at their multiplicities. So x is just a straight line, passes straight through the xy intercept. X cubed, however, is this wiggle. It flattened out in the middle. So actually, we've already seen this flattening trend. We've just not talked about it. So if we were to have something like x to the 91st degree, what we're going to notice is it's really going to flatten out between -1 and 1. So this should be just above the x-axis here. But it's going to look very, very flat as opposed to the line that just went straight through. So the multiplicities, simply the number of times the root occurs, tells us a lot, tells us what happens at that x-intercept. It tells us if it crosses or if it bounces, and furthermore it tells us if it flattens out or passes straight through.